Not to be confused with Shopify. We did it first, I swear. So in data infrastructure, we basically build tools, platforms, services, whatever's really needed for data engineers and machine learning engineers at the company. And this talk mostly focuses on a diffing tool that we used pretty extensively during our migration to GCP, which we have blogged and spoken about publicly before. And we also use it pretty regularly during backfills or any other major internal migrations. The talk is kind of split into two parts. First, we'll talk about the tool itself, and in the second part, we'll have a bit of a tangent into writing expressive code, and I will try not to get too preachy, so bear with me. Cool, it's working. So this talk mostly focuses on Big Diffie. The simple explanation is it's a data pipeline that produces a statistical diff between two data sets. It's intended for big data usage, so we use it on Google Cloud Platform to diff Avro and Protobuf data sets on GCS, as well as BigQuery. It's written in another open source tool called Shio, which is a data processing framework that was developed in-house. And it's basically a Scala wrapper for Apache Beam. If you're not familiar, you can think of Spark for Google Cloud Platform. And this tool, Big Diffie, is part of an open source library we have called Ratatouille, which contains a few other pieces, including Scala check generators for different data formats and a sampling pipeline as well. And it can be imported as a CLI, installed through Brew, or you can import it as a library and use it in your projects. So we'll cover quickly what's involved in a diff. So we need comparison by key. So we need some sort of key in order to compare records on the left and the right-hand side. And the record will be comparing on a record level. So record A on the left-hand side will be comparing to record A on the right-hand side. And in order to do that, you need to boil down to the field level and compare field to fields and produce deltas, so that a delta is basically the difference between field 1 on the left hand and field 1 on the right hand side. And once we have these deltas, you can also get the distance between them, so that we know exactly how far off we are from the between the left hand and the right hand side. So this sounds very vague, so let's look at some actual examples. This is the actual output of the tool in GCS. So it can output tab-separated values or output to BigQuery if you want to do analysis and some querying on the output. So on a record level, this is what it produces. Basically, for every key, it says if it's the same. So in this case, record key 1 is the same on both the left and the right hand. Record key 3 is missing on the left-hand side, which means it was found on the right but not on the left. And record 2 is different. And then there's a bunch of these values after. We'll explain these in a bit more detail in the next couple slides, but the first value is the name of the actual field that a difference was found in. Then you have the left and the right-hand values, and the type of the value, which is string. The last value is the distance between them. This is what it looks like on a field level. So this is another piece of output that it produces, and this is basically across a single field for the entire data set. What was the difference? So if we have a field called myKey, and we encountered this field 10,000 times, 50.125% of them were the same. These numbers are completely made up, by the way, so if they don't make sense, I'm sorry. Delta type, so the delta type basically says, the delta type is inferred from the type of the field. So a numeric delta type means it's a numeric field. Min and max are the min and max distance. And I'll explain a bit later on how these distances are actually calculated. Mean is the mean distance across all differences, and then there's the moments about the mean later. If you're not familiar with them, there's extensive documentation online. I don't have time to go into them in this presentation. But basically, there are things that describe the shape of the curve and how far apart different fields are in terms of distance. And the last one is pretty simple. On a global level, it also outputs some counts. So if we have 100,000 records, 80,000 of them were the same, 15,000 were different, and 5,000 are missing on the right-hand side. This is just, so the general premise is you look at these global stats. If everything's the same, okay, cool. Or maybe not if you expected some differences. And then you can start diving into these field level stats to figure out where exactly the problems might be, and down to the record level if you need to look at concrete examples. So these distances, where do they come from? Numeric, I hope you would guess that that's for numbers. And that's pretty simple. It's just the absolute distance between x and y. We also calculate the Levenshtein distance, which is basically the edit distance for strings. So I put some examples here. From kitten to mitten has an edit distance of 1 because you change one character. From grip to gripe has an edit distance of 1 because you add one character. And similarly, going the opposite way would be removing one character. And so it's basically a metric to tell you how far away one string is from another. And the last one is the cosine distance, which is for vectors. And the calculation is laid out there. Basically, if you have two data sets where you recalculate some vectors, you want to know how far apart they vary, we use that calculation. There aren't other calculations for distances provided, but if a need comes up, they can also be added. And we'll dive a bit into the code here. This is how we actually represent delta. And we basically just need to define a delta to pass it around for context. And we do left and right-hand side comparison. We produce these deltas and delta types. The delta types line up with these distances that I showed earlier. And we'll dive into how these are actually used on the next slide here. So if you're not familiar with data processing code, don't worry too much. I'll try to explain it. So you see, we basically look at the fields and do this iteration across all fields for every single record. I've actually trimmed down some of the edge cases in this just for readability. But this is an example of diffing Avro records. And it's pretty simple if you actually look into it a bit more. Basically, it says if it's a record type, we need to do some actual casting because Avro is a bit nasty to work with, and then do a recursive call to diff. If it's a repeated type and it's unordered basically means with a list, you can't always expect to read it in the same order with Avro. It's just the way the data format works. So we want to do a sort and then do the comparison after. And otherwise, we want to compare the left-hand side and the right-hand side and produce one of these deltas. Okay, and then we'll get a bit further in. So how are these deltas actually used? So there's a decent amount of code here, but the premise is that we use the distance to calculate these moments in the first half, and then we produce this map that basically maps a field, delta type, the minimum, maximum distance, and the moments. And the moments are these values at the bottom here: variance, standard deviation, skewness, kurtosis. And in the second half, we basically convert a diff type to a vector so that it's easier to sum them. And then we output this tuple of this vector and this map, and we call this sum. But what is the sum actually doing? Well, that goes into semigroups. How many people are familiar with semigroups? Raise your hand. Okay, not too many. So it's okay because it sounds scary, but it's actually a super simple thing to explain. And the premise is semigroup. If you look on Wikipedia, you end up with this complicated definition of there's a set and some operation, associativity, and then you start like a couple links down, you're buying 3 lambda calculus textbooks. It sounds super scary, but in reality, if you look at this code, it's pretty simple. So we're doing this combine operation that basically does a reduce function on the semigroup. So it takes one thing, takes 2 things, puts them together, makes one thing. pretty simple, and it can be parallelized because it's associative. Everybody with me? Great. And like a coworker of mine said, 50% of data engineering is basically adding things. So defining semigroups is actually quite useful. So you can see in this sum here, we're actually calling this on a vector of longs and a map where the map is, the key is a long and the value is an option of all these things, right? But we just have to call this simple sum operation. And that's because using semigroups, we can actually get some of this knowledge that people have encoded into these operations. So the first block here is actually written into our code base. And the second two come from Algebird, which is a algebraic operation library provided by Twitter. And this is actually a lot of contextual knowledge that we kind of get for free just calling the simple sum. And it makes our code super easy to read, right? So it seems like something that's useful. So maybe we can leverage this to make our code more expressive. So I'll walk through an example of the code base that I showed earlier. Just it'll be a bit contrived, but I'm trying to use the same code base just so I don't have to introduce new code. We can do this kind of thought experiment where if we wanted to make this, we have this diff type vector. And this is kind of ugly to look at. You have a bunch of ones and zeros, and it's hard to tell like what the difference is between lines sometimes. The spacing's not quite the same, etc. And so for the sake of example, let's say we were providing these diff types to some downstream user. In my case, I'm writing libraries that other people in the company are going to consume. And we want people to be able to understand our code and not be confused by it. So for example's case, let's say we split this off and we created a new diff type that represented an aggregate diff type. And here we have this function that provides a way for us to convert some existing diff type to our new aggregate diff type. And we provide a semigroup for this that basically dictates the rules for how we're going to add a left and a right-hand side. Then, if you take our previous example, we're basically stripping out this entire vector operation and abstracting it away from the user. And all the user has to do is create this aggregate diff type, pass it in, and call a sum. And then we can even potentially go one step further. So this is kind of a magical slide because I couldn't fit the actual code in this. But let's imagine there's this diff types module that we provide to our user. And we say, OK, if you want to use this diff types, all you need to do is import this packet or this object. And whenever you use a diff type, your sum is automatically provided for you. Because we're the ones writing these diff types, we create the rules for how they can be added together. And all the user has to care about is the fact that they're using them. And they don't need to care about how they're combining these operations. And so we can encode a lot of this contextual knowledge that we have and abstract it away from the user without them having to think about it. So in conclusion, I think things like semigroups or monoids, which are kind of like semigroup, except there's a zero. These are very simple concepts in algebra, and they seem scary, especially to people that just go online and start looking at random links. But we can explain them in very practical ways. And if you use them in practical ways, it's not so scary. You can explain them in ways that regular programmers can understand. And readable code is good, so we should strive to have that. That's about it. Does anyone have any questions? Yes?
Dumb question. What's an S collection?
Sorry, I should have explained that. You can think of it like an RDD or something like that in Spark. It's just it's an object that basically represents a collection of a single data type. So let's say an S collection of string represents think of it as like a parallelizable list. So it's a list of string that can be parallelized over multiple worker machines. And so you can provide, similar to how you would map over a list, let's say you map a list of ints to strings, you could do that same thing in an S collection and run it on multiple workers.
Is that for scale or for scale and speed?
Both. It's similar to how most data processing frameworks work.
Your cosine distance, is
Yes.
that something that you use for measuring the distance between, say, arrays or vectors?
Yeah, specifically for vectors, it assumes that the order in this case, it assumes that the order of the vectors actually matter because they map to a specific dimension.
And these vectors would be vectors of certain numeric types?
Yes, yes. Over there.
How are you using this, or are you using it in your data science pipeline to keep track of the data drifting? So does it impact your models?
Yeah, good question. For those that didn't hear the question is how are we actually using this? The vast majority of our use is fairly simple. It's comparing backfills. So a lot of times, let's say an artist looks at their play count for a track and they're like, hey, this looks kind of weird. All my other tracks on this album are really high, and this one track is really low. Why is that? Sometimes things like this flag that we need to actually look into this data and understand what went wrong. And sometimes we find issues that we then have to patch. So in cases like this, it's very difficult to say like how you can't expect the data to be exactly the same. So you need to understand like how much did the data actually change, and then why is that the case? And so by providing these statistical numbers, you can actually get a better understanding of what effect it had on your data, and then use that to say whether or not your change made is a step in the right direction. Yeah.
Follow-up. So are you using this offline batch process, or is this an online production kind of thing?
Yeah, so most cases this is offline batch process. I think there's 1 or 2 cases where people are running this repeatedly day after day, but I think those are much rarer. For the most part, this is after some major step, people are running this to do some verification. Yes?
How common is the knowledge and understanding of like monoids and semigroups in your sort of data work?
Yeah, so that kind of leads into what I was getting to alluding to at the end. Most people, they don't, I would say like there are a subset of people that have like good understanding of these things, but for most people, they understand it in a practical sense, but not necessarily like in terms of category theory or what the mathematical laws are. So for the most part, it's about, especially in our case, we're providing libraries to hundreds of other data engineers in the company, and we can't expect everyone to understand all the math behind it. So we need a way to introduce these concepts in a way that people understand them practically and can still leverage them in their day-to-day work. Other questions? Yes?
What's the roadmap?
The roadmap is, that's a good question. I would say right now it's not under active development. I'm mostly continuing to support it, but we're, I guess, fairly agile in terms of support. If there's a lot of demand for very specific things, we can discuss. And the whole project is open source. I add a link at the bottom here. And my email is listed there, as well as my Twitter. I don't actually tweet, but you can use it to contact me if you need to. Yes?
Seal and Beam have different runtimes, right? Like they can run on Spark or Datafrog.
Yes.
At Spotify, do you all use the same runtime? And can you say what that runtime is?
For the most part, we run on Dataflow.